Muy buenos días a todos, bienvenidos al taller de conversión y almacenamiento de energía. En esta ocasión tenemos este taller organizado por la División de Conversión y Almacenamiento de Energía, liderada por el doctor Javier Rodríguez Varela y el doctor Ismael Verde. Ellos nos hicieron el favor de organizar y de contactar a las personas que van a estar impartiendo este taller el día de hoy y de mañana. Entonces les agradezco bastante su apoyo y toda su paciencia en este proceso de organizar el evento. Como todos ustedes saben, tuvimos algunos problemas técnicos hace 15 días y por eso reagendamos el taller para el día de hoy. Es para mí un gusto tener a todas las personalidades que impartirán este taller y no me cabe la menor duda que será un taller muy enriquecedor tanto para los asistentes estudiantes como para los profesionistas. Hay personas de mucho renombre en este taller que van a impartir estas conferencias el día de hoy y el día de mañana y les quiero dar la más grande de las bienvenidas a este evento de la Sociedad Mexicana Electroquímica. Entonces, para inicializar este evento tenemos al profesor Lee, del cual el doctor Rodríguez Varela nos dará una semblanza y después tendremos su plática. Muchas gracias a todos por asistir, sean bienvenidos y espero que este taller cumpla con todas las expectativas que nosotros nos hemos propuesto. Muchas gracias. Adelante, doctor Rodríguez.
Gracias, doctor Cabral. Buenos días a todos. Antes de presentar al doctor Lee, una forma de cómo vamos a operar, cómo está organizado. El doctor Lee no puede quedarse toda la sesión, entonces le pedí que dejara unos minutos para preguntas y respuestas, comentarios. Y desde las siguientes pláticas, no va a haber preguntas al final de cada presentación, sino hemos decidido mejor dejar un tiempo, una mesa redonda le hemos llamado, para abrir una discusión al final de media hora, como para interactuar un poco más todos los participantes, crear algo de debate tal vez. Entonces, después de cada presentación, no habrá preguntas, sino al final les pedimos que guarden sus preguntas para la última media hora, ¿no? So now I'm going to introduce Dr. Lee. He's an assistant professor of materials engineering, and he's a distinguished professor, William Dawson Scholar at McGill University. He obtained his undergraduate bachelor degree from Seoul National University and PhD from the MIT in 2015. He also did a postdoc at Berkeley University, uh, University of California at Berkeley from 2016 to 2017, and another postdoctoral research at MIT 2017 to 2019. His research interest is discovering sustainable battery materials based on experimental and theoretical research. He also was a finalist of the Science Award Electrochemistry by Volkswagen BASF, and he received a project just from an agency in Canada under the name of Discovery Accelerator Supplement. He has made critical contributions to developing high-energy cathode materials for lithium-ion batteries, leading to his publications in top journals. He has published in Science, Nature Chemistry, Joule, and Advanced Materials, all of them of high impact factor, of course. He leads the Jinfinity Energy Lab at McGill University, and he is a scientific advisor of Neo Battery Materials Limited in Canada. So with this impressive background, we welcome Dr. Lee. Dr. Lee, go ahead, please.
Okay, so thank you very much for the very kind introduction of myself. So I will begin my presentation. So good morning, all. First of all, it's my great honor to have a chance to participate in this storage and conversion of energy workshop of the SMEQ. So today I would like to give a talk about the materials and electrode engineering for high energy cobalt and nickel-free lithium-ion batteries. So to begin with, let me first briefly introduce what I do for research. So I'm a materials engineer interested in both experimental and theoretical study to develop advanced battery materials, in particular for the lithium-ion batteries. And we know that there are many battery components, including cathode, electrolyte, anode separator, etc. And right now, like my group is focusing a lot on the cathode and the electrolyte. I'd like to give a lecture about this cathode component. So to start with, let me briefly go through the basic operating principle of the lithium-ion batteries. So in the lithium-ion batteries, we know there are cathode and anode that can store and release the lithium ion and electron during charging and discharging, and they are immersed in the electrolyte. Now, upon charging, the lithium ions and the electron in the cathode side migrate to the anode, resulting in oxidation at the cathode and reduction at the anode. And now upon discharging, the reverse reaction occurs. So from this simple operating principle, we can know that a good electrode material is essentially a nice home for the lithium ions and electrons. So to develop a good electrode materials, electrode materials must have many available sites for the lithium ions and electrons per unit volume or per unit weight. And also, the lithium diffusion and electron conduction within the crystal structure of these electrode materials must be fast, such that within a given time period, a large amount of lithium ions and electrons can occupy their site, leading to high charging and discharging capacity per given time period. So with this simple, and in this respect, there has been a legendary class of cathode materials from which nearly all high-performance cathode materials have been developed for the lithium-ion batteries, which are called layer rock salt type lithium transition metal oxide, in particular, those that utilize the nickel and cobalt as the main transition metals. So in these layer oxide materials, lithium and the transition metal forms alternating layers within the cation sublattice, and the oxygen forms the close pack lattice. And now, this material could deliver very high capacity owing to this 2D lithium diffusion pathway in the lithium plane and a two-dimensional transition metal plane, such that the lithium ions can easily go in and out of the cathode structure along with the electron conduction. But unfortunately, these materials are typically made of a large amount of expensive and heavy cobalt and the nickel, which makes the cathode the most expensive and heaviest component in the lithium-ion battery. For example, now if you look at the materials cost, there are in total about 6 to 7 components in the lithium-ion batteries, and the cathode alone takes over nearly 50% of the total material cost. And because this cobalt and nickel are heavy, heavy species containing a lot of this in the structure, make the cathode also the taking over nearly 33% of the total mass of the lithium-ion battery. Therefore, considering all, we can imagine that the performance of the lithium-ion batteries, as well as the cost of the lithium-ion battery, largely is determined by this cathode material. And in addition to this, nearly 70% of the cobalt is currently mined in the Republic of Congo, where unethical mining practices are widespread. So this represents the unsustainable lithium-ion battery development. So overall, the researchers have agreed on the need to develop high capacity, but cobalt and nickel-free cathode materials for the sustainable lithium-ion batteries. And in this regard, today I would like to give an overview of the materials called disorder rock salt type cathode materials, in short, DRX cathode materials for high energy nickel and cobalt-free lithium-ion batteries. So here I'm showing you the crystal structure of the DRX structure. And in these materials, lithium and the transition metals are near randomly distributed within the cation FCC lattice, whereas these anions, such as oxygen or fluorine or sulfur, forms the anion FCC lattice as well. So you can consider these materials as brother materials as the layered Roxel cathode materials, as I discussed earlier, because they're both classified as Roxel material, crystalline material. But unlike the layer Roxel, where they're like clear ordering of the lithium and the transition metal, in this material, lithium and the transition metals are randomly distributed. So we call this disorder Roxel. And interestingly, this material can deliver very high capacity above 300 milliampere per gram and very high energy density above 900 watt per kilogram, which are much higher performance compared to the traditional nickel and cobalt-based cathode materials. And finally, the most important part is that these DRX materials can be made with many different types of inexpensive and abundant transition metals, such as manganese, titanium, vanadium, or iron. So considering both the inexpensiveness and also the high performance, these DRX materials are a few class of materials that can actually bring a substantial improvement to the lithium-ion battery development. So based on this introduction, I would like to give an overview of the DRX material and the future research direction. First, by going through the materials level understanding of these materials, which includes the discussion about the lithium diffusion process and the electron storage process called redox process. And also, I'm going to discuss the remaining challenges and opportunity to develop these DRX materials at the electro and the cell level. So let me first talk about the materials level understanding of this material. So the first part is about the diffusion. So historically, these DRX materials have been neglected as the cathode materials for a very long time because they tend to show very poor performance. For example, here I'm showing you the voltage profile of the lithium cobalt oxide on the left side as the structure changes from the layer Roxel structure to the disorder Roxel structure by the process called cation disordering. And now in this type of profile, the x-axis is the capacity, the amount of the lithium-ion electron this material can reversibly store and release, and the y-axis is the voltage. And now if you look at this voltage curve, we can see that the charge storage capacity of the lithium cobalt oxide dramatically decreases as the structure changes from the layer to the disorder Roxel structure. And people have been explaining these poor performance of the disorder materials with the slow lithium diffusion process in the structure. And people have argued this happened because with the cation disordering, the lithium diffusion barrier dramatically increases such that the lithium diffusivity exponentially decreases. And also, people have argued that the randomly distributed transition metal cations in this DRX structure can physically block the lithium diffusion path as well. And note that based on this understanding, people have been trying to avoid any kind of cation disordering in the layer structure, which leave us no choice to use both the nickel and the cobalt because there are a very few possible metals that can actually stabilize the layer structure with the reduced amount of the cation disordering for fast lithium diffusion. So overall, these DRX materials have considered the poor lithium diffusion materials, so they have been neglected as a cathode for a very long time. But in 2014, me and my colleague developed an interesting new materials called lithium molybdenum chromium oxide with this particular composition, which challenges the conventional wisdom that the disorder Roxel materials is a poor cathode material. So this material is very interesting because it initially forms as a layer Roxel structure, but as you can see from this XRD pattern, but it transformed almost completely to the disorder Roxel structure after a few charging and discharging cycles. And this is evidenced by the dramatic change of the XRD pattern from that of the layer to the disorder Roxel structure. And it's also seen from the scanning transmission electron microscopy image that shows the dramatic change of the layer Roxel contrast. You see the layer contrast here, but to the disorder Roxel contrast. So the conventional wisdom would then expect very poor cyclic performance of this material. But surprisingly, we found that this material can deliver very high capacity up to 260 milliampere per gram cycling around 1 lithium per formula unit, which was remarkably high capacity, considering that the typical well-layered lithium transition metal oxide cathodes such as the lithium cobalt oxide delivers around 160 to 190 milliampere per gram. So what these results actually propose to us is that, in fact, the disorder roxyl materials can be an interesting high-capacity cathode materials, and this means that, in fact, the lithium diffusion in the disorder roxyl structure can be fast under certain conditions that people did not realize before. So to understand this counterintuitive behavior, we did some theoretical study using both density functional theory calculation and the Monte Carlo simulation. And then in this study, we found there's like a general lithium diffusion pathway, and we realized that there are geometrically, there are 3 types of diffusion channels, namely 2TM channel, 1TM channel, and 0TM channels. And in this naming scheme, this name refers to the number of the transition metal cations next in the phase sharing with the tetrahedral lithium, which becomes the activated lithium diffusion site. So here, so wait for a second. Never mind. So, but now, so here you see the 2TM channel, you see 2 transition metal, and the 1TM channel, there are 1 transition metal there, and 0TM channel means there's no transition metal around this diffusion pathway. And what we found from the DFT calculation is that both the 2TM channel and 1TM channels are barely active in the DRX structure, but we actually have a channel called 0TM channel, which allows the lithium to jump around the neighboring lithium site. So what we found is that if the population of the 0TM channel is a lot, so that if the 0TM channels start forming a giant network within the disorder roxyl structure, then basically, because the 0TM channel is active, if they start percolate, the lithium diffusion can continue to take place through this active 0TM channel uninterrupted by other inactive channels, so that the diffusion in the DRX structure can be fast. And what we found from the Monte Carlo simulation is that in order for this 0TM channel to occur, the disorder roxyl materials have to be made into so-called lithium excess materials, where the lithium excess stands for the composition in which the number of lithium sites is greater than the number of transition metal sites, such as the lithium 1.2 transition metal 0802 composition. Right here is there are extra lithium over the transition metal, so there are much more lithium than the transition metal there. We call it a lithium excess, and we found that if these DRX materials are made into lithium excess composition, then this 0TM channels start to percolate, so this material can become very high capacity material. And this basically explained why this lithium chromium oxide could deliver high capacity, whereas the traditional DRX materials have shown poor performance. For example, the traditional DRX materials were made into non-lithium excess material like lithium 1, iron 102, or lithium nickel titanium half-F. This like transition metal total is 1. So lithium 1 transition metal 102, they're non-lithium excess material. So the 0TM percolation is there. There is no such 0TM percolation, but now this lithium chromium oxide, as you can see from this composition, this is a highly lithium excess material, and therefore the 0TM percolation occurs to lead to high capacity. So based on this simple understanding of the lithium excess composition unlocks the lithium diffusion process in the DRX, many people in the world have started to develop various nickel and cobalt-free lithium excess DRX cathode material, delivering very high specific capacity above 300, even like 600, 360 milliampere per gram. And some of them start to achieve high energy density above 1,000 watt per kilogram, and which are really like remarkably high number, considering that the typical traditional cathode material stores around 700 watt per kilogram. And note that here the DRX material, because now we don't have to worry about the layer structure, we don't have to use this expensive nickel and cobalt, and we can basically use all kinds of the transition metals in the periodic table, so we have a large chemical space to explore. Okay, so but I would like to say that we need to further study the lithium diffusion mechanism in this disorder reaction materials, and also we have to further study the effect of the lithium excess composition to the performance of the DRX material. And in this regards, like recently, like people have understood that in fact in the disorder reaction material, instead of the lithium and the transition metal completely randomly distributed, people have found out there can be some kind of local show range order, which can influence the lithium zero TM percolation, therefore the lithium diffusion in the structure. So these things have to be further understood. And also recently, I've shown that the particle sizes become actually very important when we determine the necessity of the lithium excess to develop high capacity DRX cathode materials. And in this paper, I show that in fact, we don't need lithium excess for certain kind of the DRX material when they're made into nanoparticles. So I would like to say that overall, there must be more fundamental understanding about this lithium excess effect and the lithium transport mechanism. So with that, now let me change the gear and now discuss the redox mechanism. So how does this kind of material store electron and release electron during charging and discharging process? So in the traditional cathode materials, there are the transition metal content is very high, and this transition metal serves as the electron storage reservoir. For example, let's look at the lithium cobalt oxide, the traditional cathode found in everywhere. Now we have the composition of lithium 1, cobalt 1, O2. Now imagine we extract one lithium from the structure. What happens is that as we extract one lithium ion, we also need to extract electron from something. And this electron actually comes from the cobalt 3 plus in the structure, getting oxidized to cobalt 4 plus. And with this oxidation, there's a release of the electron. So in this traditional material case, we can see that the number of extractable lithium in the structure is same as the number of extractable electron from the transition metal oxidation, right? But unfortunately, if you look at this lithium excess disorder structure composition, we can know that this balance will be broken. So for example, let's imagine we have the composition of the lithium 1.2 transition metal or 802 composition. Now, from here, we can already know that there are nearly 50% more lithium compared to the transition metal in the structure. And now let's imagine we want to extract all these lithium ions from the structure to achieve high charging capacity. But what happens is that typically the electrons coming from the transition metal oxidations are often not high enough. And typically in experiments, only 0.4 lithium out of 1.2 lithium can be extracted using the transition metal oxidation, leading to the transition metal specific capacity of around 120 to 140 milliampere per gram. So if we want to extract the remaining lithium from the structure, then we need additional electron source, right? So where do we get this electron? We get this electron from the oxygen getting oxidized. So this is the reason why to operate this lithium excess DRX cathode, it is important to understand both the transition metal oxidation, or say reduction, combining we call it redox, right? So it is important to understand the mix and oxygen redox process to actually achieve high charging and discharging capacity, right? So then the question is this: can this oxygen redox reversibly add extra capacity for the DRX cathode beyond the transition metal oxidation capacity? This is the first question. And then now, and experimentally, it was found that indeed this oxygen redox can additionally take place in the transition metal after the transition metal oxidation. But now the question is, how does this mixed oxidation of the transition metal and oxygen occurs during charging and discharging, right? So to understand this fundamental question, we performed the theoretical study, and in particular, we tried to study the effect of the local structure around oxygen atoms in the DRX structure to the oxygen redox activity. So imagine the DRX structure like I said, the cations are nearly randomly distributed in the cation FCC lattice. So, and it is interpenetrating with the oxygen lattice. So we can imagine that there can be many different types of local structure around oxygen. So for example, here on the left side, we're left top part, we are seeing the oxygen atom in the middle. This is denoted with the red atom here. And there can be a local structure on oxygen where there are 3 transition metals in the transition metal layer. I mean, that's here in the layer side, layering, and then you can find another lithium ions in the nearby. And also you can, but now in the disorder rocker structure, we can imagine that the occupancy of these sites are nearly random. So we can imagine that there are many different types of local structure around oxygen. And now, when we think about this electron getting oxidized or whatever, that requires the electrons to be at a decent energy level. So it is possible to extract electron from that particular level. If the electron is too stable, then that electron will not be extractable upon charging. And we know that this electron structure around oxygen or other transition metal will be largely determined by the local structure around this oxygen atom or transition metal anion, cation. So we can imagine that all these different oxygen atoms may react differently upon an oxygen redox process, right? Because the local structure is different, resulting in different ligand field, okay? But now, if you look at this configuration, we found that there are too many, right? It's difficult to understand. So in this paper, to simplify this, we boil them down into 2 possible scenarios with the perspective of the oxygen 2p orbitals. Now, we know that oxygen as anions have a 3 2p orbital, right? We have 2px, 2pz, and 2py, right? So now we can have 3 branches of the oxygen atoms, oxygen 2p orbitals. And now if you carefully look at this configuration, we can see that first of all, there can be oxygen 2p orbitals lying along this particular lithium oxygen to metal or metal oxygen to metal direction. And because now these oxygen 2p orbitals have one end, at least one end have the transition metal there, and the transition metal has also the orbitals as well, right? So what happened for these particular oxygen 2p orbitals lie along this like metal oxygen, they start to form a hybridized state. So you know from the chemistry 101, after this hybridization, you're going to generate a higher energy anti-bonding hybridized state. And we're also going to, at the same time, we're going to have a low energy hybridized bonding state. And what happened for these oxygen 2p orbital is that they start to become the low energy, very low energy, stable oxygen 2p orbital after the hybridization. And because after this hybridization, the oxygen 2p energy of this particular orbital are too low, they will not be able to get extracted upon charging, right? Charging is like extracting electron from some species, and these electrons are the too stable ones. So it takes so much energy to remove this electron from this oxygen 2p orbitals, so they cannot participate in the oxygen redox process. But now if you look at the remaining geometry, we can find that actually there are oxygen 2p orbitals lying along this particular lithium to oxygen to lithium directions that we name as the lithium oxygen lithium state. And because the energy of the lithium state is too high, basically they do not hybridize with the oxygen 2p orbital. And because of the lack of the hybridization, what happened is that the oxygen 2p energy orbital's energy becomes more higher compared to this hybridized oxygen 2p state. So they become more chemically labile. They become more ready to engage in electron extraction from the oxygen. So I hope you understand so far. And so based on this simple chemical intuition and combining with this ligand field theory and the density function theory calculation, I'm not going to detail. And what we found in that indeed this oxygen 2p orbitals along this lithium oxygen lithium state are the oxygen or electron that participate in the oxygen redox process to give extra capacity beyond the transition metal oxidation capacity, so that we can control the population and the spatial distribution of this particular lithium oxygen lithium state to determine this oxygen redox activity of the lithium X DRX materials and also other type of lithium excess transition metal oxide cathodes, such as layer lithium excess NMC cathode, basically because they share the same crystal structure overall. They're the broader structure, so the same principle happened. So this was the basic understanding of how this mixed transition metal and the oxygen redox process can happen in this cathode materials. And this paper has been cited close to 1,000, almost already like above thousands, has become a very important paper in this field. So, and I would like to say that the one that I described is purely theoretical study, but in fact, we are continuously studying this combined redox mechanism using both some like soft X-ray absorption spectroscopy or the hard X-ray absorption spectroscopy, because they can actually analyze the real electronic structure of the structure, this cathode material during charging and discharging. And so we can understand this experimentally, and also we can actually use density function theory to further investigate. And basically, I've been doing this further study to understand like when does this lithium oxygen lithium state oxidation trigger a different type of oxygen oxidation mechanism, including oxygen-oxygen dimer formation, forming superoxide or peroxide in the DRX structure. Because like forming different version of the oxidized oxygen species can affect the operating potential of the DRX and the cycling kinetics. So we don't have to worry about it. If you're interested in, just read the paper. But anyway, I would like to say that more studies need to be done on this DRX material to make this material better. But now, okay, so for now, I've been talking about the lithium diffusion, which is possible with the lithium excess composition. But at the same time, I discussed that because of the lithium excess, we now have to rely on the both the transition metal and the oxygen redox process. And what we found is that because of this, actually, like we enter into some critical issue, which is related to the oxygen redox related side reaction. So, for example, here I'm showing you the voltage profile of the two different DRX compounds, which are lithium nickel titanium lithium oxide and the lithium manganese niobium oxide. And first of all, if you look at the left voltage profile, we can see that the charging and discharging curve looks very different, right? They're asymmetric. So this shows that there are some intrinsic voltage hysteresis coming from some like weird redox mechanism. And also now, if you look at the right voltage profile, we can see that although this lithium manganese niobium oxide deliver very high capacity up to 300 water per kilogram in the first cycle, but this capacity quickly drops to less than 170 milliampere per gram only after 20 cycle, which basically shows the poor capacitor retention. So we see that there's a lot of cycling stability and the cycling performance issue even after we designed this disorder oxygen material with some interesting strategy. And we found that this is largely due to this excessive oxygen redox process that happened in the DRX material, which triggers a bunch of the structural degradation. So for example, on the left side, I'm showing you the oxygen loss profiles, the gas evolution. And the middle part, I'm showing the in situ XRD pattern of the DRX lithium nickel titanium molybdenum oxide. And now if you look at the left curve, we are looking at the gas evolution upon first charging. And in this profile, the black one is the first charging curve, and the red curve is the O2 gas evolution. And now if you look at this, we can see this, upon first charging to above 180 milliampere per gram, now we see that there is a significant amount of O2 gas detected from this cathode, meaning that there's an irreversible oxygen loss coming out of these materials to change this overall composition. And this happens because the oxidized oxygen tends to be unstable in this oxide lattice. So they, instead of staying in the crystal structure of the cathode, they rather leave to the electrolyte. So that's one evidence of the side reaction. And now if you look at this middle profile, this is the ET2 XRD patterns of the lithium nickel titanium oxide during first charging and first discharging. Now we can see that this 002 reversible shift of the peak, meaning that there's an irreversible cation rearrangement in the structure to show result in bulk structure degradation. So obviously there are some like a critical failure of this material, and also we found that surface can irreversibly change into new structure, leading to some poor performance of these materials. So overall, like excessive oxygen redox in DRX have shown to trigger structure degradation. So based on this understanding, I tried to come up with some strategy to prevent against some oxygen redox related side reactions, prevent this oxygen redox related side reaction. So I came up with several different strategies, including fluorination, which means that you replace some of the oxygen 2 minus anion with the fluorine 1 minus anion. So we call it fluorine substitution for oxygen or fluorination. And this is one strategy. And another strategy is called high valent cation substitution. And here, this high valent cation is the niobium 5+, or the molybdenum 6+. So the oxidation state of this metal is simply high. So we call it high valent. And finally, I also studied the so-called surface immunization. So it's a treatment that's just to passivate the surface against oxygen redox related side reaction. But instead of going through all, I'm going to just discuss the combination of the fluorination and high valent cation substitution to show that we can actually fight against this oxygen redox related side reaction. So basically, combining this fluorine substitution and high valent cation substitution with the given lithium excess composition, we can actually maximize the transition metal capacity. So we don't have to rely much on the oxygen redox, so we can avoid this oxygen redox related side reaction. So for example, let's imagine we have some lithium excess DRX material which rely on the 120 milliampere per gram from the transition metal redox and 140 milliampere per gram from the oxygen redox. Okay, in this case, there will be a lot of oxygen redox related side reaction. So what if we can change the composition so that although this is still the lithium excess material, we can increase the transition metal capacity to, let's say, 220 milliampere per gram. So upon achieving 260 milliampere per gram, we can only rely on the 40 milliampere per gram. So to avoid this oxygen redox related side reaction. So considering this, I'm going to explain the so-called manganese 2+ to manganese 4+ double redox process in the DRX structure to demonstrate how we can maximize this transition metal oxidation capacity in the lithium excess material. So let's imagine we have the lithium excess manganese oxide with this particular composition of lithium to manganese O3. So if you renormalize this composition, we can rewrite this composition into lithium 1.33, manganese 0.67, and O2. So this is essentially 33% lithium excess material. So it's a highly lithium excess material. And now in this material, it is a highly lithium excess material. So the diffusion through the zero TM percolation may be fine. But now if you look at the manganese oxidation state, the manganese oxidation state is already manganese 4+ at the discharge state. And now in this kind of oxide structure, manganese 4+ is considered the highest oxidation state that the manganese can take. So if you want to extract all this lithium from the Li2MnO3, basically you can never get any electron from the manganese oxidation. So you basically have to completely rely on the oxygen oxidation process, right? So this is bad, right? I say because I say too much oxygen oxidation is bad, right? Because it's trigger side reaction. But now let's imagine we replace one of the oxygen ion 2 minus ion to the fluorine 1 minus anion. Now, right? Instead of O3, we go to the O2F composition. Now, because of the total anion valence has changed to 6 minus, right? Oxygen is 2 minus, times 3 is 6 minus. But now if you go to the O2F, now the total anion valence is 5 minus. So the total cation valence also has to change from 6+ to 5+, right? So to get this, now in this manganese oxyfluoride, now the manganese oxidation state start from manganese 3+. Now, because of this, now if we extract lithium from the structure, we can at least get one electron coming from the manganese 3+ to manganese 4+ oxidation, right? So we certainly get some capacity from the transition metal oxidation. But now we can do this even further by substituting high valent some of the manganese 3 plus cations with the high valent cations such as niobium 5 plus and titanium 5 4 plus, because if you include such a high valent cations, the remaining cations, including manganese, has to decrease its oxidation state. So if you do this with this particular composition, you can actually push down this manganese oxidation state from 3 plus to 2 plus. So if you look at this composition now, in this case, the manganese starts from manganese 2 plus. So if you charge this cathode, now you can extract 2 electrons coming from this manganese 2 plus to manganese 4 plus double redox couple, right? So based on this idea, in this, go into the lab and synthesize 2 different type of the manganese double redox possible compounds, which are lithium manganese niobium oxyfluoride and lithium manganese titanium oxyfluoride with this particular composition. And now again, this material can utilize 2 electrons per manganese atoms. And because now this manganese oxidation capacity in this highly lithium access material is large, we found using hard and soft X-ray absorption spectroscopy and density function theory calculation, we found that the manganese capacity is so large, so the oxygen oxidation capacity is minimized. So because of this, we found that even up to the charge of the 5 volts, now you're also looking at the right side, the gas evolution profile. We said there is a basically negligible amount of the oxygen gas evolved from the structure. By the time of this paper was published, this was a very interesting result. So this means that we can significantly reduce this oxygen redox related side reaction. And as a result, we found that we can significantly improve the stability of this manganese-based DRX cathode material. For example, on the left side, I'm showing you the typical voltage curve of this lithium access manganese disorder oxide material. With you see the large voltage hysteresis and fast capacity loss. But now if you look at the voltage curves on the right side and the middle side, we see that the voltage hysteresis is significantly reduced, and this voltage hysteresis coming from the oxygen oxidation. So we found that voltage hysteresis is largely removed. And then the capacity retention was also become much better. And then we found using XRD that the irreversible structure degradation is substantially suppressed. And we also found that these materials can deliver very high energy density even up to 1,000 watt per kilogram if you go up to very high voltage charging like 5 volt, which is not practical, by the way, which was much larger energy density compared to what the typical traditional cathode materials can store. But I would like to say there are other issues to further address for these materials to become ever practical cathode. For example, these materials are made of the manganese, and then we know that the manganese tend to dissolve in the electrolyte. So these additional problems have to be addressed. But this paper basically showed that we can actually control you can engineer the redox process in these kind of materials to achieve a novel cathode material. So, and I would like to say that the chemical space of this nickel and cobalt-free DRX cathode materials are really, really large. And now people have developed the so-called partially disordered DRX material as a partially disordered spinel that deliver ultra-high capacity above 360 milliampere per gram. And interestingly, we found that in 2020, the group of scientists in the UC San Diego developed DRX lithium vanadium oxide anode instead of the cathode that have been developed so far. So I would like to say that the chemical space of this disorder oxide materials are very, very large. And in fact, like this chemical space is so large because now instead of sticking onto the single phase compound, we found that actually we can make these DRX material into nanocomposite multi-phase heterogeneous compound to further expand the chemical space to achieve higher specific capacity and higher capacity retention. I'm not going to go into detail because the time is ticking too fast, but I would like to say that instead of staying into single phase, we can further move on to the multi-phase chemical space to achieve very high capacity. So there are a lot of exciting new opportunity on this material. Okay, so now let me try to briefly go through the remaining challenges and the opportunities to address to develop the DRX material. So I would like to say that so far the stuff that I discussed is really about the material itself. Imagine I've never discussed about this particle morphology. I never discussed how the electrode is developed, how this particle size is, or whatever, right? So people have been in the field so far, people have been largely sticking to understanding the intrinsic property of the materials without actually considering the practical electrode or cell level study, right? But I'd like to argue that the electrode and cell level study is very critical to overcome the remaining issue related to the capacity fading and impedance growth happening at the electrode level or the cell level, which is different from the intrinsic property of the material. One thing I would like to show today is that actually it's a critical problem related to the low active materials content that in the electrode film that people have been used to demonstrate good performance of this DRX material. So we know that the cathode materials or anode materials are electrode film, be it cathode film or anode film, they are made of at least three components, right? We have an active material like DRX, and we have to put conductive carbon or some other type of conductive additive, and then we also need to put binder, right? But so far in the literature, people have been diluted this electrofilm, which means that you put a lot of conductive carbon and the binder, or you put a very small amount of active material. So in the realistic cell, the active material content has to be close to, let's say, 96 weight percent. So only 4 weight percent are the conductive carbon and the binder. But in the literature, what is known is that the active material content is only sticking to, let's say, only like a 70 weight percent. So which is far from being ever practical. So even if these materials deliver very high energy density per particle, because the content of this particle in the electrode is very low, so you don't really get energy density gain at the electrode or the cell level, right? So we need to actually see what kind of issue will be happening if this DRX material start to be included in the practical electrode and the practical cell level, right? And so we've been working on this practical electrode and cell level study. And what we found is that although I've never discussed in the previous slides, what we found that the electrical conductivity of these DRX materials tend to be much poorer compared to the traditional cathode material. So this caused a lot of problems when we try to increase this active material content to the practical electrode composition. For example, here like I'm showing you the electrical conductivity for many different type of lithium excess DRF compound. And what we found is that the electric conductivity is in the order of the 10 to the negative 7 or 10 to the negative 10 centimeter Siemens per centimeter, which is much lower compared to the value from the NMC nickel manganese cobalt type layer cathode, which is like 10 to the negative 3 Siemens per centimeter, or even poorer than the lithium iron phosphate, which is another cathode material known to be a poor conductor. And because of the low intrinsic conductivity, we found that if the active material content becomes very large and large, meaning that the conductive carbon amount becomes much, much smaller, we found that the performance becomes significantly poor. For example, here I'm showing you the voltage profile of so-called partially disordered DRX material. Now, if this active material is 70% and the carbon black is like 20% and the binder is 10%, now we see that the performance is largely impressive, like delivering close to like 360 milliampere per gram with decent capacity retention. But now if you go to like an 80-10-10 electrode composition, so now you have lesser amount of conductive carbon, more amount of active material. Now we see that the reversible capacity becomes smaller and the capacity fading is much faster. And we found that if you go to even like a 95.5, which becomes more to the typical composition, we found that the reversible capacity becomes much smaller and the capacity becomes very poor. Retention becomes much poorer as well. And finally, I would like to say that this type of phenomena is kind of universal for many different type of DRX material, including another type of DRX material. It basically also like if it's 70-20-10, cycle well. If it's go to like 80-10-10, perform poorly. And now 95-5, you basically cannot cycle this material at all. So this is very universal. So this low electrical conductivity becomes a very important problem. And what we also found is that now, besides this like low electric conductivity, we found that the manganese DRX materials typically exhibit like a 5 to 10% volume change during charging and discharging. And then with the pulverized nanoparticle morphology, basically what happened is that during charging and discharging, the electrode start to disintegrate. So for example, now here I'm looking at the cross-section or SEM image of this 80-10-10 electrode material. And here the white part is the DRX material, and the gray part is like this carbon black. And now if you look at the cross-section, this is the before cycle electrode. Now, if you cycle 5 times, now you start to see pores generating from the cross-section, and you also start to see crack is developing across the electrofilm. And now if you go to 80-10-10, after 20 cycle, now you see the pores start to agglomerate, and you start to see a large crack develop across this electrofilm. So this all this problem has to be addressed at the electrofilm level. So I would like to say that I have some solution to this, and I'm under revision. But anyway, like this type of study must be further done to develop practical electro level cell. But I would like to say that there are like electro level way to improve this performance. So there's you can rest assured. And I would like to say that in addition to this, it's very important for us to come up with a scalable production method of morphology controlled DRX particle, because like current DRX materials have been synthesized, cannot mass produce morphology controlled particles. And what happened is that typically people use so-called solid state synthesis followed by particle pulverization or the mechanochemistry, which also involve particle pulverization. So in the end, you basically produce pulverized particle. You barely cannot control the morphology, so you cannot apply uniform coating, or you can also like exposed particle surface can also greatly expedite this capacity loss. So we need to come up with new synthesis method and processing method to come up with more like a morphology controlled DRX particle. So at McGill, we are currently developing universally applied DRX synthesis method to address this issue. And finally, I would like to say that many of the DRX materials deliver high energy density when it is charged to about to very high voltage up to 4.8 volt, which is beyond the stability window of the conventional electrolyte. And I've discussed that the oxygen oxidation generate oxygen radicals that can attack the electrolyte, and also there can be some transition metal dissolution problem. So overall, we have to say that there must be some compatible electrolyte to further address this issue. So our group is also working on this type of direction research. And I would like to say not just me, but also some other people in the field like try to address this kind of electrolyte level issue by coming up with some like novel electrolyte. So with that, I would like to summarize my talk. So today I would like to show to you that the DRS cathode can lead to nickel and cobalt-free high-energy nickel lithium-ion batteries for sustainable energy storage with higher energy density and lower cost. And the key idea is that the lithium excess composition is critical for lithium diffusion in the DRX structure by introducing so-called zero TM percolation. And I wanted to show that because of the lithium excess composition, we need to rely on the mixed transition metal and oxygen redox process, but this needs to be carefully engineered to achieve a high capacity with minimum capacity fading. And finally, I would like to show that the electrode and cell level studies are critical beyond the material level study for the DRX materials, the practical installation in the lithium-ion battery. With that, I would like to acknowledge my funding sources and the collaborator, and thank you very much for your attention, and please ask me whatever the question you have. Thank you very much for your kind attention.
Thank you. Thank you very much, Dr. Lee.
Thank you.
We have a time for some questions. I'm not sure how are we going to do, Dr. Cabral. Shall we allow assistants to open their microphones? Or if you have any questions, you can raise your hand. I don't see any. Okay, there is a question in the chat. Can this strategy be used for sodium batteries? It is a question from Vladimir.
Do you hear me? Do you still hear me, right? Yeah.
Yes.
Okay, so yeah. So that's an interesting question. So we hope that this DRX structure is also possible for the sodium-ion battery, but generally it is more difficult to make disorder rock sodium-ion cathode because when you think about the disorder or the layer, this kind of cation ordering happens to lower this crystal energy. And what happens is like if you want to promote this disorder, it is kind of more favorable if the alkali metals such as lithium or the sodium to have a more similar ionic radius to the transition metal. Now, in the disorder rocker, the lithium ion and sodium ion is much bigger ions compared to the lithium ion, right? And the transition metals are actually smaller ions compared to the lithium and the sodium. So the ionic radius difference between the sodium and the transition metal are smaller. So they have a less energy penalty when they try to make a disorder with the help of the high conservation and entropy. But sodium ion case, sodium ions are much larger ions. So instead of they start mixing each other, which generates some like a lattice distortion, they rather like to form some kind of layer structure. But it depends on what kind of transition metal you use, because some transition metals, the ionic radius may be still large enough to accommodate disorder with the sodium as well.
Okay, there is another question from Emmanuel. Is it possible to use perovskite structures in order to generate the all redox processes?
So it depends on what type of oxygen redox process you're talking. I mean, like if you're talking about using perovskite as a lithium ion cathode, or if you talk about the perovskite as a catalyst, I don't know what's but it depends. Assuming you're trying to use some perovskite structure for the lithium ion battery cathode, I think it really depends on the your composition, because sometimes if your perovskite is made with a large amount of the transition metal, then before oxygen redox ever get happening, basically the transition metal will basically take over the electron storage. So even if you want this oxygen oxidation to take place, but that's it's nothing. I'm like, you cannot happen. But again, this oxygen redox process is dictated by the local oxygen environment. So I will have to dig into the local oxygen environment around perovskite. But if in the perovskite, if all the oxygen 2p orbitals are hybridized with some metal, then the oxygen redox process will take place less. Okay.
Thank you. Yes, thank you. There is another question from Dr. Erika Bustos. Thank you so much, Professor Lee, for your nice talk. What is the thickness of the best films that exchange lithium and contain fluoride?
So first of all, so you're talking about the oxyfluoride cathode, right? I think that you're talking about the film made out of the lithium, manganese, whatever oxyfluoride, right? They are just a single compound, right? Just the lithium and the fluorine is just like atomistically mixed in the crystal structure. So I think like that depends on the electrode composition. If you make the diluted electrode with lesser amount of active material, you can increase the thickness much larger. But if you start making a more higher active material content electrofilm, then the maybe high thickness, large thickness may not be preferable, because it's not. There are a lot of complicated issue happening at the electrofilm level, so it is difficult to say like what is the best thickness. But the thickness of the best film, like so far, we can go up to let's say 40 micrometer, or like to 60 micrometer. So I think that's possible.
Okay. There is another questions from Dr. Iván Alonso. Thanks for your nice talk, Dr. Lee. In your opinion, what kind of cathodes have more future in large-scale production? Sulfur-based cathodes or cathodes that you show during this talk?
Yeah, this is a very interesting, important question, and I also thought about it. But when you talk about the sulfur cathode, you're talking about the lithium sulfur batteries. Okay, assuming I think when you talk about the large scale production or the fate of the battery technology, I think like you have to see it in the cell level at least, not just the cathode level. So of course, in practice, like in theory, sulfur-based cathode will outperform all the available cathode materials. But you know that to operate the sulfur cathode, you typically people use the lithium metal anode, right? And if you think about the lithium metal anode and the sulfur cathode, and then assuming some level of a thickness, what people have predicted is that the gravimetric energy density of the lithium sulfur battery can be greater than the lithium ion battery's gravimetric energy density. But people have already calculated that, in fact, the volumetric energy density of the lithium sulfur battery will be poor compared to any kind of the lithium ion battery using different type of cathode. So it will really depend on the application. Because if you think about this application where the volumetric energy density is less of a concern, then you go with the lithium sulfur battery. So sulfur cathode is important, but on other cases, you're going to use the lithium ion. But if you think about the lithium sulfur battery, assuming using the lithium metal anode is possible, then in fact, you don't have to work on the sulfur cathode. You can just use the lithium ion cathode and you just replace the graphite anode with the lithium metal. Then your lithium ion battery system will also suddenly show much higher energy density. So I think it's like we have to be very fair when we talk about this comparison. Okay.
Thank you, Doctor. We have one last questions because of the time from Fernando. Maybe with the perovskite structure and doping it, you can get more oxygen vacancies and can have more oxidative sites?
Oxygen vacancy and oxidative site. I have no. I really need to see what composition you're talking to make any clear statement. But based on your statement that if you generate oxygen vacancy, that means like somehow your structure is somehow reduced, because we know that I don't know. So I think like when we talk about the oxygen oxidation, when we talk about the oxidation process of the existing oxygen, right? Instead of the oxygen vacancy does not have oxygen ion there. So like there's nothing to oxidize for this particular site. So yeah, but that's a good question, but I know I have no clear answer about it. Thank you.
Okay, thank you, Dr. Lee. I guess we have to stop here because of the time. I'd like to thank you very much, Dr. Lee, for your very nice presentation. And this is a very important research at the moment regarding batteries, rechargeable batteries. So thank you very much. I don't know if you have any comments, Jose or Ismael.
Thank you, Dr. Lee.
Thank you. Thank you.
Just trying to share this important new issue to batteries. So it's too glad to hear you. I think for our students, very, very important to know what is the state of the art of this field. Thank you so much, and hopefully I see you soon, Professor Lee.
Thank you very much. Thank you so much. Thank you. Okay.